Good evening. Can you hear me?
Yes.
Okay. So whoever can, please switch on your video so that we can have some feel of a real classroom, if possible. So I want to get started with a reminder that project one is going to be due by Canvas on October 30th or earlier. That is, you have to submit through Canvas. So for that, I would like to point you to the syllabus, which I have posted on the Canvas that I keep updating after every lecture. So I've given the submission instructions here. What I would specifically want you to do is to write your handwritten solution. It can be typed up or it can be written and scanned, and put it in a PowerPoint file and submit that along with plots generated using your code. That is, in the same PowerPoint file, please put the solution and the plots generated like you would do for a paper, like a method section and result section. And then your implementation, that is the code or script that you wrote in either MATLAB or some other language, please upload that code, submit that. Sometimes the format may not work out. So you could submit that as a zip file or as a text file, preferably in a file that can be directly downloaded and I can run it in MATLAB. What I definitely want you to do is to write your own subroutines for computing the power series. This is practice for you to implement the function or the infinite series that you see in the Bessel functions or Legendre polynomial. I think mostly the problems I've suggested are problem 1 to 9 from problem set 5.5, which are involving Bessel functions of the first kind and second kind. So I want you to implement them, and the script must be submitted. And the submission is most importantly through Canvas, not by email or paper copy. It is computer controlled. So if you don't submit by 5:30 p.m. on October 30th, you will lose your chance to submit. So please don't be late. Just submit it on time. I won't give any extensions in general. Okay. If anyone wants to do a different problem other than what is suggested, you are welcome to approach me and we could have a discussion. But my uh, uh, goal is to have you use the Bessel function of second kind, self-study that, and then implement that as a solution. That's why I picked these problems for the project. Okay. Any question about the project? Okay. Moving on. So I have for today's lecture, I'm going to be writing on PowerPoint slides, which you can see like the whiteboard, and then we'll have discussion and examples like we usually do. So today I plan to start with Fourier transform, which is covered in section 11.9. Towards the end of last lecture, we talked a little bit about what does the frequency content, or how is the frequency content related to the Fourier series in general. And here is Fourier transform, which directly gives you the spectrum or the frequency content of a function or a signal. And today I plan to go through these topics, and then on Monday I would like to wrap up this module with examples on Fourier series, generalized Fourier series involving Legendre polynomials and Bessel functions, as well as Fourier transforms. So that from next Wednesday, the plan is to start with module 4, partial differential equations, and then we have the fall break, so there is not a lecture on the following Monday, but from the following Wednesday, we'll continue with that. Okay. PDEs is one of the longer topics in this course, so I plan to talk about it until October 30th, which is also the day of your submission for project one, and then exam two is planned for November 4th. Okay. All right. Moving on. So we want to start with the definition of Fourier transform, about which a very simple definition or derivation is given in the book, but it's not a very mathematically rigorous definition, which they also note in the book. So I'm not going to go through the derivation and directly going to start with what we know, maybe some. So can you please mute if you are going to be having any background noise? Thank you. If you have any questions, please feel free to talk. But if you have any background noise, I would appreciate if you can mute. All right. So we start with the Fourier transform, which is given as f with a tilde of w is 1 over square root of 2 pi minus infinity to infinity f of x e power minus iwx dx. Sorry, dx. There is a derivation that is given in the book, which loosely starts with the idea of Fourier series and then arrives at this formula. But it is only like a suggestive definition and not a rigorous definition, which we suggestive only, we skip it here. What we are essentially starting off is by saying W is a frequency parameter and the Fourier transform is a mapping from real space, which could be spatial or temporal, to frequency space. Okay? Real space to frequency space. All right. So we have the formula for the forward transform or the Fourier transform, which is an integral of f of x multiplied by the frequency parameter w integrated over the entire range of x, which is minus infinity to plus infinity. The inverse transform is also obtained. Again, we are not going through the derivation. The inverse transform is f of x equal to 1 over square root of 2 pi minus infinity to infinity, the Fourier transform e power iwx integrated over w. So this goes from frequency space to real space. So a compact notation is introduced in the book, which is to write the Fourier transform of f of x is denoted as f of f. This is the Fourier transform, and the inverse Fourier transform is denoted as f inverse of f tilde. So you can write this is equal to f tilde, this is equal to f. Okay. So let's just start with some examples trying to get familiar with this formula, find the Fourier transform of f of x equal to e power minus ax. That is, this we define the function f of x as e power minus ax for x greater than 0 and is defined as 0 for x less than 0. Sorry, x less than 0. Why? Because e power minus ax goes to infinity if x is less than 0. So we make a finite valued function by defining the function to be exponent of minus ax for positive x and 0 for negative x. And of course, a is a positive number. A is a parameter which is a positive number. So can you try using the formula? Maybe we are using this after some time. So if I say f of f tilde equals f of x, this is equal to 1 over square root of 2 pi minus infinity to infinity f of x e power minus I wx dx. Can you carry out this integration, please? Oh, wait. Sorry, I skipped over one step. So we talked about the piecewise definition of f of x, right? So this integral has to be written as this is 1 over square root of 2 pi minus infinity to 0, 0 times e power minus iwx plus 0 to infinity e power minus ax e power minus iwx dx. I mean, this is, since we are doing it for the first time, it would be helpful to keep sense of the integration limits correctly to ensure that this is a convergent number, which is 0, and then we'll evaluate the other integral. Okay. So adding on the slide. So this is 1 over square root of 2 pi, 0 to infinity, e power minus x times a plus iw dx. 2 pi e power minus x times a plus iw, and I have to divide also by minus of a plus iw from 0 to infinity. If I am skipping to the next slide too quickly, please tell me. Of course, I'll post these slides and the recording as well. Okay. All right. So the upper limit clearly is 0 because e power minus infinity is 0, and the lower limit would be 1 over square root of 2 pi 1 over a plus iw. So this you can write a minus iw divided by square root of 2 pi times a squared plus w squared. Just multiplying and dividing by the conjugate of the denominator, the complex conjugate of the denominator, which will give me a squared minus I squared w squared in the denominator. Since I squared is minus 1, we write the denominator to be a squared plus w squared. So
I think you forgot the negative sign.
negative sign. So when I substitute the lower limit, I have 1 minus of a plus iw, which gives me 1 plus 1 divided by a plus iw. What did I forget here? I'm sorry, what was the problem?
I'm not sure, but I think there should be a negative sign in the denominator. Not sure.
Negative sign where? Negative sign where?
In the after the integration, where you
Yeah.
substitute 0. So before that, there's a negative sign, and after that, there's oh, no, no, no,
Okay.
no, no, no. That's correct. That's correct.
Okay.
Correct, and it's correct to say.
All right. Okay. So we have f cap of w or f of f equal to 1 over square root of 2 pi a minus iw divided by a squared plus w squared. So the real part of f cap happens to be 1 over square root of 2 pi a divided by, oops, sorry, my iPad PowerPoint app just crashed. I don't know what happened. Okay, we didn't lose too much. So uh, yeah, all right. So this is f of f, which is equal to 1 over square root of 2 pi a minus iw divided by a squared plus w squared. So the real part of f cap is 1 over square root of 2 pi a divided by a squared plus w squared, and the imaginary part of f cap is 1 over square root of 2 pi minus w divided by a squared plus w squared. Of course, I'm counting on you to know a little bit of complex numbers of what is real number, what is imaginary number, and for a complex number, the real part and imaginary part. These are things I'm just assuming you would know. Okay. All right. So just to, again, just one more example before we look a little bit about the properties of the Fourier transform as well as its physical interpretation. Let's go to problem set 11.9 and pick one example to try out. Okay, something that challenges your integration skills, perhaps. All right, problem 9 from problem set 11.9. Problem set 11.9. Problem 9. So this is f of x is defined as the absolute value of x or magnitude of x for -1 less than x less than 1 and 0 otherwise. So if we write the Fourier transform as a function of the parameter w, which is f of f, this is square root of 2 pi. I might as well write -1 to 1, the absolute value of x times e power minus iwx dx. Okay, so our Fourier transform is square root of 2 pi -1 to 0 minus x times e power minus iwx dx plus 0 to 1 x e power minus iwx dx. Obviously, the goal of uh, doing Fourier transforms is to get the frequency content or the frequency spectrum, which we are going to see shortly. But can we do something about the integral so that we can simplify it instead of having to do the integral twice? Is there any tricks that you can pull to keep this a little bit easier or simpler? Can you do some transformation to make this simpler? Just thinking, okay, I'm not sure of the answer. So if I say -1 to 1, the function is looking like this. And your e power minus IWX parameter, where W is a number greater than 0, because it's a frequency, it has to be a positive number. Uh, this is, how does this function vary in this interval? This is 1. Is there any way these two integrals can be equal to each other? Probably not, because this function is not symmetric about 0. So I don't think it would be easy to simplify. So let's just go ahead and do the integration. F of W equals 1 over square root of 2 pi. What is the first integral? -1 to 0 minus x e power minus IWX dx. Um, can you write down what is x e power minus IWX dx as a formula, which will make things a little bit simpler for us? So this will be minus IWX times x divided by minus IW plus 1 over IW integral of e power minus IWX dx. So these are the kind of minute details that you want to keep practicing, because if you could save a couple of minutes in the exam with your integration skills, that would help you get more time and think more clearly. Okay, so I would strongly again urge you to practice. Okay, so this is uh, x e power minus IWX divided by IW with a negative sign plus 1 over IW e power minus IWX divided by minus IW. So this is minus x e power minus IWX. So this is minus 1 over I squared W squared e power minus IWX, which is okay. So can I move on to another slide, or I'll wait for a minute? Did I do this right? Any mistakes? Because that will be bad. Plus IW plus 1 over IW e power minus IWX dx. And then I have minus x e power minus IWX divided by IW plus 1 over IW e power minus IWX. Okay. Okay, looks correct to me. If you think there is something else, please let me know. Okay. All right. So I'm going to go back here and write this is equal to e power minus iwx divided by w times minus x over I plus 1 over w. This minus x over I can write I times x. And I have to apply this limit between 0 and minus 1 or minus 1 and 0. Okay. So we have minus 1 to 0 of x e power minus iwx dx equal to uh, e power iwx divided by w times ix plus 1 over w from minus 1 to 0. So what is the upper limit? Upper limit is 1 over w, uh, 1 over w squared minus e power iw divided by w minus I plus 1 over w. Looks messy, okay? I'll tell you that. And then we want 0 to 1 x e power iwx dx, which is e power minus iwx over w, ix plus 1 over w from 0 to 1, which would be minus 1 over w squared. And what do we need? We need the negative of the first expression plus the second expression. That is our integral. I'll take a 30-second break here. Tell me if we are right so far. Okay. So continue. F of w equals 1 over square root of 2 pi. I have minus 1 times 1 over w squared minus e power iw over w minus I plus 1 over w plus the second expression is e power iw or minus iw divided by w times I plus 1 over w minus 1 over w squared. So I have minus 2 over w squared plus e power iw over w you can see how tedious these integrations can be. Are we together so far? Ayush, good. Jeffrey, wait. Is my audio working? Can you speak now? Arash, am I audible?
Yeah. Yes.
Okay, I can hear
We can
you,
hear you.
but okay, I wasn't able to hear Ayush or Jeffrey, so I got scared.
Okay,
Okay,
is this working?
now I can hear you. Yeah.
Hello?
Okay. All right. So one step closer.
Okay.
All right. So our Fourier transform is 1 over square root of 2 pi times I have minus 2 over w squared plus 1 over w. I'll write 1 over w times or actually I'll write this as minus 1 over w uh, e power iw minus e power minus iw. And then I have plus 1 over w squared times e power iw uh, plus e power minus iw. And since we know something about this e power iw and e power minus iw, we'll write this as which again will take the 2 outside. Square root of 2 by pi 1 1 1. What is this what is this expression? If you know, go back to Euler's formula. E power iw is cos w plus I sin w, and e power minus iw cos w minus I sin w. So you can recognize this as sine of w, and you can recognize this as cos of w. So our expression finally comes down to Fourier transform is square root of 2 by pi uh, minus 1 over w squared minus sine w over w plus cos w over w squared. Okay, is this function or is this expression defined at w equal to 0? Or in other words, if I ask you what is this value, what would you say? Is this finite valued at 0 frequency? That is the question. Come on, say something. First of all, in this course, you have learned the necessary tricks to answer this question. You heard about Taylor series, you heard about Maclaurin series, power series, and simplifying or expressing any function as a power series. Given that knowledge, can you rewrite this function in a way that you can actually evaluate its value at W0? At the face of it, if you just substitute W equal to 0, you get the first term go to infinity. The second term, it does not exist because it is 0 divided by 0. And the third term also goes to infinity. So you would be tempted to say that this expression is not defined at w equal to 0. So to answer that question, you want to express the various terms as a power series. So what is sine w over w? What is sine x series? You know this. W minus w cubed by 3 factorial plus w to the fifth over 5 factorial and so on, and then divided by w, which gives you a 1 minus w squared over 3 factorial plus and to infinity. You also have cosine of w divided by w squared, which is 1 minus w squared over 2 factorial plus w to the fourth over 4 factorial and so on, divided by w squared. I think by now you would have guessed the answer, or you would have seen the answer, which is 1 over w squared minus 1 over 2 factorial plus w squared over 4 factorial and so on up to infinity. So if I ask 1 minus 1 over w squared plus 1 minus w squared over 3 factorial plus w to the fourth over 5 factorial and so on up to infinity plus, damn it. Okay, okay, good, it's still there. So this is, I have to go back 2 steps, w squared over 4 factorial and so on up to infinity. So I have 1 over w squared, or actually minus 1 over w squared minus sine w over w plus cos w over w squared. So this is minus 1 over w squared minus 1 minus w squared by 3 factorial plus w to the fourth over 5 factorial and so on, plus, and then third term is 1 over w squared minus 1 over 2 factorial plus w squared over 4 factorial minus up to infinity. So this term and the first term go cancel each other, and I have minus 1 minus 1 half. This is minus 3 by 2. What is the next highest power? I have plus w squared times 1 over 3 factorial plus 1 over 4 factorial plus w to the fourth multiplied by something and so on and so forth. So the value at w equal to 0 happens to be minus 3 by 2. Why that becomes important is, now we come to the so-called physical interpretation of this Fourier transform. The Fourier transform of a function, which we write f of f, which is formally defined as square root of 2 pi minus infinity to infinity f of x e power minus I wx dx, represents the relative importance of a frequency w. Okay? More specifically, minus infinity to infinity f of w squared dw represents the total energy of the signal or system represented by f of x or f of t if it's a time domain problem. We'll write minus infinity to infinity f multiplied by f conjugate dw. Because this Fourier transform can be a complex function, so we'll take the function multiplied by its conjugate to represent the total energy of the system. So if we say this is total energy, what is the energy contained in a particular part of your spectrum? So if you take any range of frequencies, suppose W1 and W2 are two frequencies. W1 to W2, F cap and F cap conjugate, dW represents the energy contained in that bandwidth. Okay. So very often frequency domain analysis is done using to analyze dominant processes in a time dependent system. I mean, it could also be spatial frequencies, but generally we associate frequency with time. So we say time dependent systems. Okay. Just a question for you. When I say dominant processes, in what aspect am I referring to the word dominant? What is dominant about it? When we have a signal and we say a dominant process or something that is uh, the most important process or frequency happening, in what way are we saying the word dominant here? By what metric it is considered dominant? Okay, since you won't say, we are this integral I told you represents the energy content in that bandwidth, right? So we are just trying to identify which band of frequencies or which frequency in particular contains the most amount of energy. Suppose a particular frequency has an amplitude and that amplitude corresponds to say 99% of the total energy, which means it's mostly the only process and then everything else is just 1%. So when I say dominant, I'm referring to with respect to the of energy, fraction of energy contained in that frequency or bandwidth. Okay. Some properties of Fourier transforms. Convergence. So we have f cap equal to square root of 2 pi minus infinity to infinity f of x e power minus I w x dx if f of x is analytic without conditions, then f cap of w exists. If it is analytic, meaning it's finite valued and continuous, and it is going to be integrable, and which means this integration can be performed and the Fourier transform does exist. Second property, linearity. So the Fourier transform of AF plus BG is simply equal to hold on, I'll write this as F. So the Fourier transform of a linear combination of functions is simply equal to the Fourier transform of f multiplied by a plus b multiplied by the Fourier transform of g. It's very easy to prove because integration is a linear operation. This proof directly follows. We'll again see, when we do Laplace transform after exam 2, almost all these ideas carry over. So what we are seeing here, Laplace transform is another type of integral transform. Most of those will simply carry over. Fourier transform of a derivative is equal to IW times the Fourier transform of the function. Again, proof is very easy. If you try doing the integration, you can easily prove this. So I'm not going to spend time on that. And you can keep doing this to write the Fourier transform of the second derivative is equal to minus w squared times the Fourier transform of the function, or the Fourier transform of the nth derivative is IW power n Fourier transform of the function. Next property is called convolution, which occurs in signals or functions that also have weighting functions which are not trivial. I'll write non-trivial weighting functions. So it's like saying the Fourier transform of a product of two functions is equal to square root of 2 pi times the Fourier transform of the individual functions. Why we wrote these properties is that when we solve problems like in your homework or your quiz, I mean, exam or whatever, you don't have to do every integration from scratch. If you can identify these one of these templates, like for example, of the derivative of linearity or of convolution, you can use that to simplify your evaluation of the Fourier transform. Like for example, if you have a table of transforms, like for example, in page 134, page 134, see, page 134, we have a table of transforms. Okay, so I'm just reading the second entry in the table. It says if f of x equal to x power a minus 1, where a is a number that is between 0 to 1, then the Fourier transform is equal to square root of 2 pi, or square root of 2 by w, sorry, 2 by pi, gamma function of a divided by w power a times cosine a pi over 2. I mean, you are of course welcome to use these tables because it was constructed by doing the integration and tabulating it for common functions. And if your goal is to get, say, for example, x cube e power minus x, you could look up the transforms of the two functions, which is the polynomial, which is line 2, and the exponential, which is given in line 3, and use convolution theorem to write the Fourier transform of this is equal to the Fourier transform of x cube multiplied by the Fourier transform of e power minus x, which will simplify your life, and which is also found in line 6. That is, the sixth line literally has this result written down for you. So between the table of transforms and the properties of the Fourier transform itself, you want to use that wherever possible to obtain the Fourier transforms of functions that may occur in your analysis of in your research or work or in this course, wherever. Okay. Any questions until so far? Okay. All right. So towards the end of last lecture, we also talked a lot about signal acquisition, signal, oops, sorry, I think it's going to crash. Sorry, my iPad is freezing. Just one second. All right. So towards the end of last lecture, we talked about signal acquisition, or what is called as sampling, and we acquire signal for a certain period, certain time t, at a sampling rate f, which is in hertz. And we did say that the fastest frequency we can that can be discerned is related to F. Specifically, it's actually F over 2. Okay. And the slowest frequency that can be discerned, slowest frequency that can be discerned is related to the observation time, specifically 1 over T. This is our example about snow in Memphis. Okay, so any measurement will lead to a finite number of observations and let's say we write 0 less than or equal to x, might as well be time, but we'll write x less than or equal to 2 pi. We will later generalize to t. Okay, so if we have signals taken at finite number of points which are spaced, so let's say we say that finite number of observation, we'll call it n observations at points that are regularly spaced at regularly spaced x values. Okay. So any measurement leads to a finite number of observations, and let's say we take them at regularly spaced x values between 0 to pi. Okay. We say that f of x is sampled at these points or x values. So you might have x between 0 to 2 pi. And let's say we have a finite number of data points, endpoints. This is what a measurement looks like. You get data points. You don't really know right away what is the relation between them or what function or pattern do they follow. And you would want to fit a function to this, or you would want to get the Fourier transform of this function, which you don't know. That is the act of measurement. So we want to write we want to determine a complex trigonometric polynomial that is essentially like a series in terms of cosines and sines, and we write q of x equal to n equals 0 to n minus 1 cn e power minus, I'm sorry, e power, not minus, I n xk, or xk. Where xk is a particular value of xk is a particular value of x. The goal of this exercise is to determine those fit coefficients Cn. So these are all fit coefficients. And we want to write down the expression for the fit coefficients so that the signal can be approximated as a Fourier series or a trigonometric polynomial. That is the goal. So then we are going to write, skipping the derivation, we are going to write Cn equals 1 over n summation k equal to 0 to n minus 1 fk or f of xk multiplied by e power minus in xk. For those who are curious about the derivation, this is given in page 529. Page 529. Okay. Right. Earlier I said something about table of integrals. Sorry, table of transforms. That was sorry, that was 534. Sorry. It was 534, not 134. I didn't see it carefully. 534. Thank you. So in page 529, we have the derivation. And then here's the expression for the coefficients, the fit coefficients. This expression or this procedure is called the discrete Fourier transform. It allows you to get the Fourier transform of a function which you don't yet know. What you have is a finite number of observations that represent the quantity you are trying to measure or quantity you're trying to measure. And this allows you to compute the Fourier transform using a finite number of observations. Okay. So if we write the signal, we'll write that as f as an array. The signal is given as f naught, f1, f2, and so on, fn minus 1, which is shorthand for f at x naught, f at x1, f at x2, and so on, f at xn minus 1. That is the signal. Okay. That is the signal. The DFT of that signal, discrete Fourier transform of the signal, f cap is a vector of the same length, okay, which we'll write as NCN, yeah, which will be summation k equal to 0 to n minus 1, 0 to n minus 1, fk e power minus in xk. So if you write that as an array, you're going to get fn is f1, f2, fn minus 1 cap, which is equal to each of which is a summation k equal to 0 to n minus 1 fk e power minus ixk. The second entry will be k equal to, I'll skip ahead to the last entry, k equal to 0 to n minus 1 fk e power minus n minus 1 xk. So you get an array of transform values which represent the frequency spectrum. Now, what you need to keep in mind is this f of f is defined at different W values. And what are the corresponding W values here? The W values or the frequency values are W equals is e power minus 2 pi n I over n, Wn. So this is the corresponding frequency values. So you would try to resolve the signal, which is originally in a space or time domain, might have some pattern. You would then transform that into a frequency domain where you have W1, W2, Wn, and you would try to get representations of different frequencies. This process is the discrete Fourier transform, where you don't need to know what is the actual function. All you have to know is a discrete set of observations and use that observation and the location of the observation in the spatial or time domain to project it into frequency domain. Real domain, frequency domain. So when you are doing your second project, this could be something that you could incorporate in that. When you get some partial differential equation and you solve it, you can do Fourier analysis on that partial differential equation on the solution. You're welcome to do that, although I'm not like strictly requiring that. But my anticipation is most of you who work in engineering, either thermal side or solid side, will encounter time domain analysis, and knowing what is DFT and then later what is FFT will be useful to you. So I'm not going to directly question you on DFT in the exam, but I think you will use it quite well. But as far as the exam is concerned, we will have at least two problems related to Fourier, this module in the second exam. It probably will involve either Fourier transforms or the generalized Fourier series. Um, I'll of course prepare a template for the exam as I'm wrapping up this particular unit. So I'll think about what are the important topics I want you to know and put that in the template. So 2 questions from module 3 and 2 questions from module 4 is my plan. Which topics will be covered through those 2 questions in each module? I'll definitely say by next Tuesday, at least I'll have a picture about this module. And then moving forward, I'll similarly think about the the module 4 and provide that narrowing down. Okay. Any questions, comments? Okay. So this FFT evaluation, or sorry, DFT evaluation is something it is very convenient for computer implementation. As you can see that it is essentially arrays of numbers and calculations. So instead of doing this on pencil and paper, I would encourage you to write your own program. All major packages like MATLAB have their DFT and FFT routines. So you can write your own program and compare it against that. That'll get you some confidence in programming as well. As far as our my original plan is concerned, I want to go back and do a few more examples on generalized Fourier series, essentially setting up orthogonality of Bessel functions and Legendre polynomials. So that is something you want to be very proficient about, as we'll use that when we do the partial differential equation. So let's go back to that. If there aren't any more questions, we want to start there, and uh, mostly all of next lecture I want to spend doing examples related to that. That clear? Like essentially you may practice section 11.6 or the problems in problem set 11.6, and those are the ones I want to focus on for almost the entirety of next lecture. Okay, so since we have some time, let's start with this problem set 11.6, problem 8, f of x equal to, sorry, not problem 8. We'll start with problem 4, something simpler. Okay, problem 4. We'll write f of x equal to x squared. Express f of x equal to summation m equal to 0 to infinity am ym of x, where ym of x is going to be the Legendre polynomial of order m. So we want to consider or calculate ams for m equal to 0, 1, 2, and so on. The hint is start or see example 1. So if you're not sure where to get started, I would start with example 1, because that explains or gives an example and you can slowly work your way upwards. Okay. So when we write x squared equal to summation m equal to 0 to infinity am pm of x, what we are really saying is this is of the form a naught times p0 of x plus a1 p1 of x plus a2, skip this, plus and so on, am pm of x up to infinity. Okay, you can look up what are Legendre polynomials of different order. P naught of x is 1, p1 of x is 3 by 2 x squared minus half, or usually it's written as 1 half times 3x squared minus 1. And what is p2 of x? You can go back to section 5.3 and look it up. Actually, section 5.2. You go to section 5.2 and page 178. Section 5.2, page 178. You have the general formula for Pn of x and sorry. Sorry, just 1 second. All right. P1 of x, made a mistake here. P1 of x is equal to x. P2 of x is half 3x squared minus 1. P3 of x is 1 by 2 5x cubed minus 3x. And it goes on. You can write in general what is Pn of x, which is given as a infinite series. Okay. So intuitively speaking, you are asked to express x squared as a function of or as a summation involving Legendre polynomials. What can you say intuitively about the coefficients a naught, a1, and so on?
think everything is zero except
Sorry.
think everything is zero except for A2.
Right. You can just look at that's correct. That is, if you look at it, you want only up to x squared. And if you look at the way the Legendre polynomials actually work, anything that is P3 or higher will have, wait, yeah, anything that is P3 or higher will have cubic powers and then the linear powers. But if you go further than P5, there are no squares. That is, everything is going to be based on higher powers only. So we can write, like he said, we can write uh, P1 A1 P1 of x. What is P1 of x? A1 x. So our term is x squared equals A naught times P0 of x, which is 1. So I don't have to write that, plus A1 x plus A2 divided by 2, 3x squared minus 1 plus A3 times P3 is again 1 by 2, 5x cubed minus 3x, okay, plus P4 is A4 divided by 8, 35x power 4 minus 30x squared plus 3. And you can keep on writing more terms. There are some things you can intuitively say there is not going to be a A1. A1 is going to be 0. Similarly, there is not going to be a A3 because those are all odd powers, and odd powers have no role in this problem because the left side doesn't have any odd power other than, I mean, in fact, it has only x squared. A4 not necessarily that A4 will be 0, but you can say that A0, A2, A4, A6 probably will be non-zero, can be non-zero, but odd powers are definitely 0. So it gives you a simplification right away that this term, this summation x squared, is m equals 0 to infinity. You can write that as am pmx, or this is m equals 0 to infinity a 2m p2mx, only even powers. Okay. So how do you go about actually evaluating the coefficients? So for that, you want to go back to our idea of generalized Fourier series, which we talked about. So AM in general for any M is going to be A to B R of x f of x times ym of x dx divided by the same norm A to B or same limits R of x ym of x dx. And we'll take R of x equal to 1, which simplifies. And for Legendre polynomials, or for y of m, in our case, ym of x equals pm of x, the limits happen to be -1 to +1. Because that is where the Legendre polynomials are convergent and defined. If we go outside that limit, they don't converge, so it doesn't make sense to use them outside that range. If you're wondering, this formula is in page 505. And this is the all important formula that you need to know, where y of m can be Legendre polynomial or Bessel functions or trigonometric functions, or any function in general. So when you prepare your sheet, this is something that should probably be there. Okay, so what is A naught? A naught is -1 to 1. My f of x is x squared. P naught of x is 1 dx divided by -1 to 1 times 1 dx. This is x cube over 3, that is x cube over 3 from -1 to 1 divided by 2. This is 1 by 3 times 1 plus 1 divided by 2, or this is 1 by 3. A naught is 1 by 3. We already kind of reasoned that you don't have to look for odd coefficients, just the even ones. So A2 would be -1 to 1 f of x, which is x squared, P2 of x dx divided by -1 to 1 P2 of x squared dx. And what is P2 of x? If you go a little bit backwards, that is 1 by 2 times 3x squared minus 1. So this is -1 to 1 x squared times 1 by 2 3x squared minus 1 dx divided by 1 by 4 3x squared minus 1 whole squared dx integrated from -1 to 1. It is bit integration intensive, but over time, as we do more integrals, this will go quicker. I have 3 minutes, so let me make sure I complete this. So A2 is equal to, can you do any simplification based on the limits and the functions we are dealing with? An even function, so that gives you some simplification. So this is 0 to 1 x squared 3x squared minus 1 dx, and then divided by 1/2. So I'll write 2, 0 to 1 3x squared minus 1 whole squared dx. It's a polynomial. So again, it won't be like a simple number like pi or e. It's going to be a actual number. So you'll need to use your calculator. Okay. So you can expand this 2 times 0 to 1, 3x to the 4th minus x squared dx divided by 0 to 1, 9x to the 4th minus 6x squared plus 1 dx. You can complete this integral. Let's just check if A4 will indeed turn out to 0. Okay. A4 would be -1 to 1 f of x times P4 of x dx divided by -1 to 1 P4 of x squared dx. What is P4? We saw that some time back. P4 is 1 by 8. So this is minus, I'll write that next page. A4 is -1 to 1 x squared 1 by 8 times 35x to the 4th minus 30x squared, correct? 30x squared plus 3 dx divided by -1 to 1, 1 by 64, the same thing squared. Obviously, this number is not zero. It's going to be some value that you'll have to compute. So it's not equal to zero. So there is a contribution to from the fourth order Bessel functions to this. In fact, what you will find is in general, A2m will not be zero, but A2m plus 1, starting with m equal to 0, is always 0. Okay. So it's time, but the plan for next lecture is do more examples related to this, especially the Fourier Bessel series as well, and also give some proofs about orthogonality. That is, we just assume that Legendre polynomial is orthogonal and Bessel function is all orthogonal. We just like we did a very simple proof for the trigonometric functions, we'll do that for Bessel functions as well, which will set us up nicely for partial differential equations starting next Wednesday. Okay, so please do examples, and we'll meet on Monday regular as we do in the class. Today was a special case. So thank you.